All right, so now we move on to lesson 22, which is energy, work, and power. And what this is it's taking our kinematics approach, our dynamics approach, and putting them together in this idea in which we talk about how energy is represented and how that energy can then be changed to give us work, and then how the work can be done over a certain period of time to give us power. And so all of these three things are collaborative, but when we look at these two pieces that we're going to bring into this, which is our kinematics and dynamics approach, you're going to see quite quickly that both of these two processes must be joined together in order to give us this definition of how energy, work, and power come together here. Now, in these two lessons that we're going to deal with, primarily lesson 22 and lesson 23, we're going to deal with first understanding what energy, work, and power are. And then in 23, we'll talk about the conservation of energy through different problems, whether they be isolated or non-isolated. Now, when we look at energy in its different forms, we know that energy can be represented in a bunch of different ways. Primarily, what we're going to deal with is mechanical energy, but it can also be represented in a bunch of different ways. And what we want to highlight first and foremost is that the idea of energy is that it is one of the most fundamental principles of all science. Energy is this idea of we're taking something and it is the transformation of physical processes. So all physical processes can be understood through the transformation of one type of energy to another. Primarily for us, just like I was saying, what we're going to deal with is the mechanical side. But when you go to Physics 30, you're going to learn about a couple different other methods of this transformation of energy. So at the 30 level, what you're going to learn is the following. You will look at more closely the chemical, radiant, electromagnetic, and atomic. These ones are all what we see at the Physics 30 level. At the Physics 20 level, what we're going to deal with is the following. So these are the ones that you're going to want to highlight. Mechanical energy, which is often designated as or denoted as EM in our unit. And it's broken up with the following types of energy. We have kinetic energy, which can be symbolized mathematically by EK equals 1 half mv squared. We can have gravitational potential energy, which can be symbolized by EP, which is equal to mgh, which is this gravitational energy or this gravitational potential, which is often due to some sort of gravitational field. And then lastly, we're going to introduce this idea of elastic potential energy, which is EP, which is equal to 1 half kx squared. So it looks very similar to EK, but when we look at kx squared, k and x are variables that we're going to get into further detail on, and there will become a further discussion of when we talk about this elastic potential energy or energy stored in a spring, k and x have very particular meanings rather than this mv, which is mass and velocity. K and x are slightly different than that. Now, again, these are the types that we're going to deal with at the Physics 20 level. So these are the ones that are important to us, or this mechanical energy. This is Physics 20. Once we build some mastery around this, then we can move forward and say, okay, now we can go into chemical, radiant, electromagnetic, and atomic. But for now, we have to have a really good foundation of the classical physics, which involves this more macro level energy types. All right. Now, moving forward, again, we're going to deal with, in this course, the mechanical energy, or as we designated on the previous page, EM. And the two different forms, just to be more specific on this, is one, we can have kinetic energy being the motional energy, or as an object has some sort of motion, it must have some sort of energy. And we designate this as EK, or denoted as EK. We then also have potential energy. Potential energy is the potential to do work. So we have this potential energy stored in some form, and it can either exist in terms of gravitational potential or even elastic, such as a spring type of energy. It can also exist in the case of a pendulum. So we're going to have potential energy stored in the case of a pendulum going back and forwards. If it's given some sort of height, we will say it's EP. And I'm going to just designate this or denote it as potential energy is EP. Now, there was a bunch of different thinkers that were the early thinkers on how we establish this change in work or this overall work that's being done in the system. Work being this idea that if I change energy forms or if there's some sort of overall change in energy form, I look at this and I say there must be some sort of work done on the system for these. And a lot of this piece here, I would recommend just reading for yourself. So just reading some of these early thinkers. Again, we're not going to really test on this, and I'm not going to go into like heavy detail on this, but some of these notes denoted in the paragraph here, just good information for the background of these things. In the case of a lesson video, if this was more of a, hey, we're going to test you on individual thinkers and we're really going to go into that idea, sure, I may ask you about this, but just for your own knowledge and for the sake of this being the lesson video, I'm just going to leave this out. You can read this on your own, just as a more of a interesting fact kind of thing. Now, as we go into the laws of energy, when we look at the two laws of energy, first and foremost, I just mainly care about this first one here, which is the first law of energy. And this one says that the total energy is neither increased or destroyed, increased or decreased, I should say. Rather, it is changing forms. So it is transforming from one type to another and from one object to another. But when we look at this, the big thing you may want to really like underline within this, if you highlight this note, is that the total amount of energy remains constant throughout this process. And what that means is even if I'm transferring from kinetic to potential energy or from potential to kinetic or some mixture of the two, kinetic and potential is equal to kinetic and potential, we may have an isolated system where it is directly transferred from one type to the other, or we may have a non-isolated system where there's still that energy transfer, but then there's work done due to heat, friction, or sound. Now, when we look at the second law of energy, the second law of energy goes into this idea that we have some sort of system where if I look at the energy transfer in the second law, energy naturally transfers from hot to cold objects, but does not flow spontaneously from cold to hot. So the example I gave in classes, I was like, well, if you have some sort of cold water that's on the stove and you put that cold water, well, it's not just going to become hot just by leaving it on the stove naturally. What we have to do is apply heat or apply some sort of energy. And through that given energy, it then becomes hot. But in the opposite case, I could take something like a hot pan and to cool it off, I would put it in cold water and we would see that that heat would naturally dissipate or transfer from the hot surface to the cold surface spontaneously. And so just through that simple analogy, we can look at this and say, yes, it's not going to go from cold to hot spontaneously, but we could see something go from hot to cold spontaneously. Now, is this one going to be very important to us? No, not necessarily. I think for the Physics 20 level, when we talk about the first law of energy, this one is going to be our critical one. But when we look at this piece here, there may be some problems in the practice notes that may refer to this, which we can definitely do once we get to our non-isolated systems. This would be maybe a law that we may use in the future. All right, now here's where we go into the specific definition of work. Now that we have a firm understanding of what type of energies there are, namely we're dealing with mechanical energy at the 20 level, what we're going to do is say, because there's some sort of potential, because there's some sort of kinetic, or maybe there's just kinetic or just potential in some cases, the work done on a system can be defined in a couple ways here. And so the principle of work is understood by two definitions. First, work is done on an object if its mechanical energy changes. So this could either be the kinetic or potential changes, and we write this according to our formula as work is equal to the change in energy. Because at the 20 level, we're just going to deal with mechanical energy, I had my students in class just write it as change in energy or change in the mechanical energy. This might be a little more specific here. And then in the note below, we just look at this and we're saying, okay, well, if it's a work is that change in mechanical energy, then it must be that work can either be defined as a change in kinetic energy or a change in potential energy throughout some sort of system. The second idea, or the second way we can approach this, is to say we can understand the work being done on a system as the amount of force over some sort of distance. And again, on our formula sheet, we see it as work is equal to F delta D. More importantly, rather than it being a science 10 type of definition like this, on our formula sheet, we actually see this version here, which says that work is equal to, and I'm just going to rewrite it in exactly the way we would see it on our formula sheet, force delta D and then cos theta. So I'm just going to change the order just slightly. Even though the F cos theta times delta D is probably more correct, if we look at it and we want to create a definition that's a little bit easier to understand, we're going to write it this way. Now, you may be thinking, okay, rather than our science 10 definition where we said work is equal to force times distance, why do we get this? Like, where does this idea come from? So to represent this, off to the side, we're going to have a box that's being pulled by some sort of force, and that force is being pulled at an angle theta. We don't know what that angle is. It could be realistically 20, 30, 40, whatever degrees. Whatever degrees that ends up being for the theta, we'll have that degree. Now, classically, what we did in the previous units, whether it be kinematics or dynamics, if the force was pulled at an angle, we broke this apart. So what I'm going to have you do in your notes is just break this apart. First and foremost, this is going to be our Fx, or the force in the x direction. I'm then going to increase this or put my vector in the vertical direction. So I'm not increasing it, but putting a vector in the vertical direction. And I'm going to call this the force in the y direction. Now, if we wanted to figure out what is the force that matters in this situation, we look at this problem and we're like, okay, this is a horizontal box being pulled horizontally and it's not being lifted off the ground or it's not being pulled through the ground. So it must be that if we have some sort of Fg, which is the weight of the object, and then because it's horizontal, we have some sort of Fn, it must be that our Fn plus Fy or Fn plus Fy is equal to the Fg. So it's all maintaining, the vertical forces are all balanced, and thus the object is not moving vertically. So it's not moving up or down. And just to be a little more specific with this force, I'm just going to elongate it slightly just because I want to make sure that we can understand the sum of Fn plus Fy is equal to the Fg. There we go. Now, that's a bit of a tangent to this, or a tangent to this derivation. What I want you to get out of this is the fact that if our vertical forces are all balanced with one another, the only force that technically causes this to have some sort of work done on this system, or the only sort of force that causes the object to move, is the Fx. And so when we talk about the object that is having work done on it, or work that's being done, it's being done by this force here. How do we get this by the definition of this triangle? Well, we know that the theta is here, the Fx is in the adjacent position. So to get Fx, we would write this as Fx equals the hypotenuse times cos of theta. And whatever that angle ends up being, that would be what we place there. And the force is often given. And so now if we translate this back to our example here, or the lesson notes, we look at this and we're like, work is equal to F cos. This is another way of saying F cos is Fx. And so realistically, we could even write this equation as work is equal to, instead of F delta D cos theta, we could just write it as Fx times delta D. Now, I will say this is the most common way this formula is written, including it's on your formula sheet that way. So I would just leave it exactly how it is right there. All right. Now, a couple notes about this piece here. First and foremost, I mean, we may as well write this in here as well because we're going to see this down the road. Work is a scalar unit, meaning non-directional, with units of newtons times meters, which is joules, and it's the equivalent of energy. So whether we're talking about kinetic, potential, or work being done, work is just the change in energy, therefore it still must be equal to joules. The second piece here, and then just to really re-emphasize that, if we know it's force, force is written as newtons, distance is written as meters. So this would give you equal to newtons times meters, which is equal to a joule. So I just really want to re-emphasize that from the notes there. Now, the couple other things that they have as a note at the bottom here is when theta is equal to 0, aka when the force is being pulled directly horizontal, we know that the cos value would be equal to 1. And the cos 0 would be equal to 1. And so I'm just going to write this out off to the side here. When they write that for that first note, theta equals 0, again, we're pulling directly horizontal with the force, meaning the theta is 0. And so I'm going to write this as work is equal to some sort of force, delta D, cos of 0, and cos of 0 degrees is equal to 1. And therefore, this would give us work is equal to F delta D. So that's how they derive that. If there's no angle, and that's the way I'm going to say it, if there is no angle or there is no sort of theta to be considered, we consider that to be where it's pulled at 0 degrees, and therefore the cos function is eliminated because it becomes 1. However, when the theta is 90 degrees, no work is done. And the reason no work is being done here is that if in the angle being pulled, or if the force being pulled, or the force that's happening, that push or pull force that's happening is at a 90-degree angle, such as this, to our given movement, then we consider no work done. And primarily, if this was being pulled vertically like this at 90 degrees, and there was no left to right movement, then we would consider it to be no work done because no distance is being covered. Additionally, the force is perpendicular to the motion of the object, therefore the force isn't contributing to that left to right motion. So therefore, no work is being done when the object is being pulled at a 90-degree angle. Okay, now if we skip forward here, we want to discuss this idea of network. Now, network just derives from the idea, similarly in terms of like net, we could call it net displacement or just displacement as an entire. We could call it net forces from our previous unit. Network is no different. Network is simply how much work is being changed or how much work is being done over the course of the problem and what is the overall result in that work. Now, again, we know that work is defined as that change in mechanical energy. So I'm going to write this as work is equal to change in E, which is equal to delta EM, just to be a little more specific. And then we can look at this, and in some notes and in some cases, we can consider work positive or negative. But this is what I would say about the positive and negative work. Because we know work is a scalar value, when we talk about work being positive or negative, just treat it as it's all dependent on the direction, and that will determine whether we say the work done in a given situation is positive or negative. And so in the case of below, they just say, let's take a look at this quick example. A barbell is being pushed up and down in a bench press. And so if we go up by some amount of distance, they consider that to be positive work. On the way down, or as the barbell is coming back down towards the person's chest, they consider this negative work. And then when you do your W net or your work net, you can add these two things together and it would cancel out to be zero. The other way of approaching this would be saying, I have work done in one direction, work done in the other. The overall work, or if I go from one spot and then return back to the same original spot, you shouldn't have any work done because no distance was covered. And I'm going to just write that as a note here below. When we look at this, the change in distance is equal to 0 meters. And if your change in distance is equal to 0 meters, you better have zero work done, because by definition, work is equal to force delta D. And if no distance is covered, all that work that would have been done throughout the problem just returns you back to the actual 0 point or to your reference point, and it doesn't matter. We can just say that work, it has to be where you cover some sort of distance with a force. And if in the end you end up back at the same spot, it just means that your work done in the system was equal and opposite in magnitude. Okay, now when we skip forward here, we want to skip forward to the work energy theorem. Work energy theorem is purely derived around the idea that we've just been talking about, that the definition of work energy theorem is that work is the change in the mechanical energy. So as we look throughout our systems, or as we look throughout the lesson 22 and 23, we're going to see that if there is some sort of change in mechanical energy from one spot to another, or from one position to another position, that is going to be representative of our work, and that represents our change in energy, which becomes the work done on the system. Now, what we care about from here is we can just do a light walkthrough of these derivations of kinetic energy, mechanical energy, and elastic potential energy. Specifically with kinetic energy and through a distance, which gives us the work, we look at the equation where, like, suppose we have some sort of cart that's here, which has some sort of mass, a force is applied, so that could be a pull force. We pull the object this way and it covers this amount of distance in the right direction. Well, we know that the work is going to be equal to the force that is pulled by its distance, or multiplied by its distance. And from our previous unit, we knew that force was equal to mass times acceleration, where acceleration is the change in velocity. That's what this piece here is in the numerator. This is representative of our change in velocity. And so we have change in speed divided by time. And then for the distance, on our formula sheet, we have this definition where our accelerated change in distance, or change in displacement, is equal to the average of the speeds. I'm even going to write that in the numerator here. This piece here, or this entire first term here, is the average speed, or average velocity. And then, so if we have the change in velocity for the first piece, we have the average velocity for the second piece, we can do a substitution of F and D in this case. When we plug those two together, we'll end up getting where, if we put this formula together, it gives us this derivation of EK, which is equal to 1/2 mv squared. Now, again, do we really need to, oh, and then the other note I would make about this is that if we look at this piece here, our initial speed or our initial velocity is typically 0. So that ends up canceling this term once we do our expansion from here. So initial speed, 0 or 0 meters per second, and then therefore the final speed is the only thing we consider here. EK is equal to 1/2 mv squared. Now again, you're not going to have to derive these things. This is more for your curiosity, or more for how do we actually get to these equations based on the idea of work. How can we relate? This is the big concept they're trying to get across here. How can we go from work and relate it to energy? That's our big thing here. Okay, gravitational potential energy. This one's a little easier. I take some mass, I increase it by some sort of height, or I give it some sort of height. That delta D, or that height that we give it, those variables are deemed the same thing. So if we look at this piece here, we can draw that tangent of delta D is equal to H. And then the mg, well, we know that Fg, which is equal to mg, is just the weight of an object. And so if this is the weight of an object, essentially what this EP equals mgh is saying is that if I take the weight of an object, which is mg, so I'm just going to underline that piece here and then draw that parallel. If I take mg and that's equal to the weight, I take something's weight or an object's weight and give it height, that's our potential energy. All right, last type of energy that we're going to introduce is the elastic potential energy. Unlike Science 10, this one's going to be very new to us. Elastic potential energy, or through a spring stretched about a distance, number one thing we want to look at here is that our delta D is going to be representative by X in these problems. So rather than H like it is in potential energy, we're going to consider the amount that the spring is stretched, or delta D, to be X. Now, Hooke's law says that if I take some sort of force, it's equal to the spring constant times the distance it's stretched. And so I really want to annotate that here. First and foremost, circle the K, draw an arrow down here, and we're going to say that the K value is equal to the spring constant. There we go. And the spring constant is always measured as newtons divided by meters, which another way of saying that in plain English is how much force does it require to compress or stretch the spring per meter of that spring. Now, the other piece, just like we were saying here, you'll want to circle your X and say the X is symbolic of the change in distance. So we look at the change in D, which is equal to X, which is equal to how much the spring is compressed or stretched, because it could be either one. And we're going to see that very shortly. There we go. Now, out of this formula, here's what we have. If we know that the force is equal to the spring constant times X, and we know that the overall work done in this situation is symbolic of force times distance, well, for this, we are going to look at the graphical relationship of how this spring works. In the case of these ones, we're going to assume that there is some sort of uniform force increase over a given distance, because what would happen is if we get this rapid change in force over a distance, then we have to use calculus at that point. So what we're going to assume is that in order to get this, we have some sort of force that is being uniformly increased as the spring is stretched. And what this says in like graphically to English is that we look at this and we're saying as the spring is further, is there's more distance, as it's either compressed by some distance or it's stretched by some distance, as that X value increases, what we're going to see is that there is more force that is generated through this process. So looking at this piece here, if we want to determine the work, well, work is equal to force times distance, or F times X. That means we're going to look for the area that represents this triangle here. The area is equal to 1/2 AB, which is base times height. In this case, the base is equal to our X value, which is the change in distance. I'm going to write it as, instead of X, change in distance. Our Kx by Hooke's law is the force required. And so this becomes 1/2 multiplied by force times distance, which is equal to Kx squared, because K is that value which we can take and separate. So K is a piece of this piece right here. Rather, if we know it's X times X, we can just combine our X's together. But what I'd sometimes like to do is just write it separately like this as Kx times X, which gives us this ability to see that Kx by Hooke's law is the force, and then the X is that change in distance, but it all comes together to give us this potential energy equation for springs. And sometimes just to differentiate, because on your formula sheet, you see EP for our gravitational potential. You also see EP for this elastic potential. Sometimes I write this as ES just to distinguish it, because I'm like, as we go forward and we're dealing with springs in future lessons, it might make sense to just treat this as the force of S. Like sometimes even in Hooke's law, on your formula sheet, I can tell you this right away, and I'm just going to arrow over here. On your formula sheet, it's written as Fs, or the spring force, is equal to, we get negative Kx as a vector like this. Now, we'll explain the negative in the future, but for now, we're just going to leave it as, we know that this is going to appear on our formula sheet. You can write that down for yourself, but we're not going to obsess over it. I will tell you more about this negative when we get to it in our future lessons, which are in the final unit, Unit D, where we start talking about this simple harmonic motion that is involved in springs. Okay. Now, the spring constant, if you want to write this note for yourself too, this is something I might want to add here, is spring constant is the stiffness of the spring. So I'm just going to write this in quotations and say it is the stiffness, which means like how much resistance is there? Does it take a lot of force to compress or stretch the spring? Is it a less amount of force to compress or stretch the spring? So we can say it's a measure of almost spring stiffness if we want, and it's different for every spring. So the example I always bring up in class is I always say, considering this situation, what if we had a car's suspension versus a pen spring? Well, the spring in the pen is going to have a lot less resistance than the one that's on the car, because if those two things had the same spring constant, then the car would just shatter. The whole suspension would break because the weight of the car is a lot more than the weight of some sort of pen. And so when we compare those two, the spring constant between different objects is going to be varying. So we got to be very, very careful with that. And again, don't worry too much about Hooke's law. Hooke's law, we're going to go into a lot more specifically. We just need to know how to use this equation through application. And then once we get to our lesson that's directly tied to springs or directly on the topic of springs, when we get to our unit D, we'll really break this down, including its visuals. Okay, now lastly, we go into power. Power is this idea that we take some amount of work, and through that work being done per unit of time, we call this a watt or power happening. So again, power, which is the rate at which work is done, the rate of energy consumption is power. And just so that we're not getting confused with the units of power, which is watts, which is W, I know that's a little confusing. In the numerator here, what we're going to do is we're going to rewrite this as P is equal to the work divided by the time. And I'm just going to put that in sentence form rather instead, or in word form. So work over time, which is equal to P is equal to the change in energy divided by time. That's another way of us seeing this here. So the amount of energy consumption per given unit of time. And then the units are in watts, which is joules per second, or energy per second of time. Now, what we can do is on our formula sheet, we're given P equals W over T. But what we can do is we can do a couple simple substitutions and derive a different formula, which is P is equal to FV. How we're going to do that is we're going to do the following. We know that on our formula sheet, work is equal to force delta D. So that's where we get that FD from in the numerator. Now, the next step they do is in order to go from here to the one below, they say, hey, we see that once we do that substitution, we have distance divided by time. Well, that's equal to speed from our formula sheet or from our kinematics unit. And so this would be unit A knowledge, if we really wanted to write that in there. Unit A knowledge says that our speed or velocity is equal to the displacement over time or distance over time, depending on the situation we're dealing with here. And this may be an alternative form for power that we want to use. Now, again, power is actually quite simplistic. So that's the nice thing, is that it's just saying how much energy do we use per given unit of time? Done. There we go. Now, let's skip forward to the practice problems, starting with the discussion questions. First and foremost, can work be done on an object that remains at rest? No, because first and foremost, it is a change in energy that causes that overall work to be done. So we look at this and we're like, by definition, work is equal to force delta D. If an object remains at rest, by first law, we're saying that it has some sort of inertia. That inertia is wanting to keep the object at rest. So not only, and this is the kind of two-part explanation we want to go into, by first law, our F net is 0 or 0 newtons. The object has no sort of applied force or no overall net force on it. So that value is 0. And then when we talk about the change in distance, well, just like it says, it's at rest. So therefore, the change in distance is equal to 0 meters. And so both of these are actually 0. So definitely no work is being done here. All right. A train is traveling at a constant speed and then makes a 180 turn on a semicircular section of the track and heads in the direction opposite to the original direction. Even though a centripetal force acts on the train, why is no work done? Now, the simple explanation would be the following, and this is the one I used in class. Create a semicircle as the following. Now, our direction of movement is going to be in the following way, where we started on one side and then we're coming back the other way or back towards the original position. What I also recommend you do is we're going to indicate a start and an end position. So here's our start, here's our end. Now, in mathematics, what we do is we call this piece here, or as I'm going to indicate here, this is our inflection point. An inflection point is where we change direction from one slope to another, or one type of rate of change to another rate of change. And so in this first piece here, if I was to ask you, I could say, what is the change in energy that is happening here? Or what type of energy form occurs in that first leg of the journey? And you would say, okay, well, it's kinetic because there is some sort of overall kinetic motion, or there's some sort of motion in the problem, meaning there's some sort of kinetic energy happening. On the way back, what we would say is, and I'm going to highlight this part in green, on the way back, I would ask you that same question, and many of you would instantly say, well, we're still a train and we're driving at this constant speed. So if we're driving at this constant speed and it's traveling there and then returning back to the same position, technically, even though there may be some sort of centripetal force happening here in this semicircle, we look at this and we say the energy on the way there equals the energy on the way back. And therefore, by definition, there is no change in energy or no change in mechanical energy. So I'm going to write that right off in the margin here. There is no work done. So no work done. And then below this, I'm going to say work is equal to the change in the mechanical energy. And if we look at this, there was no change in mechanical energy. This was equal to 0 because when we look at this piece here, the change in mechanical energy was equal to the kinetic energy on the original part plus the kinetic energy on the final part. And these are equal and opposite to one another. So these would end up canceling each other, giving us an overall energy or a change in energy of 0 joules. Because you're starting and ending at the same position, you're covering no distance. There's no sort of distance change. So realistically, you could even come at it from that lens where you say there's no sort of change in displacement. Yeah, maybe there's a change in vertical displacement, but in terms of horizontal motion and going from one place to another, you've technically expended energy and then expended energy in the reverse way. And so therefore, there's no sort of work done. All right. Now, number 3, if we look at this piece here, a book is at one end of the table and it's lifted into the air. The book is moved to the other end of the table and then lowered onto the table. Explain why there was no net work done on the book. Now, in class, the way I explained it was the following here. I had my MacBook at the front of the room, and this was the front table. And so I'm going to put my MacBook as a blue object right here, as a blue flat object. And I'll make it like this. There we go. So I'm going to just indicate that this is my MacBook right here. So in the demonstration, I took the MacBook, I lifted it up, I brought it this way, and then I placed it down over here. And so this became the new position of the MacBook, or what I'm going to call Mac number 2. Now, if this was where the MacBook was moved to, here's a thing that I want you to recognize. On the left-hand side, it had some sort of potential energy because it was above the ground by some height, which I'm going to call this is the change in height. There was some sort of height, and maybe I'll just call it height. As it sits on the desk, because it has height above the ground or above the reference point, which is 0, we're going to consider this object as the Mac to have some sort of potential energy. I lift it in the air and I bring it over to the other side, and then this has potential energy number 2. But what I realize is that it is the identical height. So realistically, at the end, I did not change anything about the potential energy. Even though I moved it across the desk from one side to the other, it didn't change its overall verticality. Therefore, it didn't change anything about the potential energy. So we know no work was done vertically. Now, some of you said, well, okay, I moved the object from one side of the table to the other, so there must have been some sort of kinetic energy. I know it. There's kinetic energy. What I want you to realize, though, is that even though there may be kinetic energy through here, and even though I've covered some sort of distance with that kinetic energy, when I look at this, I'm going to say that there's no work done, and I'm going to judge it based on this. In the original position, it was 0 meters per second, or it was at rest. So I'm just going to say it was at rest or at 0 meters per second. In the final position, it was also 0 meters per second and at rest. So if it starts and ends at rest, then I've technically eliminated all of the kinetic energy that I generated by moving the object, because it didn't say it continuously gets brought across the room and never gets placed down. We placed the object back down, meaning it went from rest position to rest position. So therefore, there should be no work done here, no net work. And I'm just going to specify that here. So no net work was done. And I'm going to express it as no change in potential energy and no change in kinetic energy. Which we know that's the case, right? When we looked at the definition of work in our notes, even go back a couple pages, if there's no sort of change in either the mechanical, or if there's no change in the overall mechanical energy, or individually there's no change in the kinetic energy or change in the potential energy, there's no work done. There could have been change in kinetic in the sense of the object could have been kept moving, but at the same height. Like, let's say the problem was this instead. I take the MacBook and I move it across the desk, but instead of stopping here, I just continue on and it keeps going at that same height and keeps going for infinity. We would look at this and say, oh yeah, there's definitely some sort of kinetic. Or even if we said it starts here and then it's moved and then it goes 5 meters at a certain speed, we could consider that work being done. And namely, in the case of this one, if it stays at the same height, we would say it's only kinetic energy done. But in the case of this one, kinetic and potential energies, neither one was changed or altered. Both of them returned to their original state, which was some sort of potential, but no kinetic energy. Okay, now we go on to our last theoretical question, which is a sailboat is moving at a constant speed. Ooh, this is a really big one to highlight right away. I'd make sure that one's highlighted in your notes. Traveling at a constant speed, which is 10 knots. Now, that's not super important to us, the 10 knots piece, so we're just going to treat it as constant speed. Is work being done on the sailboat by the wind on the sails? Okay, so first and foremost, what I'm going to draw is just a picture of the boat, and then this will maybe help us conceptualize what's happening here. So here's my water. Now, I'm no artist, so you're going to have to excuse me with this one. Just don't judge me too hard with this. So I'm going to draw the boat, which is just some sort of simple sailboat in the water. I'm going to draw the sail, which is up here, just a simple triangular sail. There we go. Now, what we know is that, yes, in order for the object to move, technically there must be some sort of overall force on the sails. So I'm going to write this as, there's our wind in the green. This is creating that force 1, or the force due to the wind. Now, this would create some sort of work because we know that work is equal to, for this piece here, because the boat is moving, we know that it is going to be some sort of force times its distance, and therefore we could also classify this as force of the wind times distance gives us that work number 1, as we're going to call it. Okay. Now, at the same time, they say that this is being resisted by, there's some sort of water that's resisting this motion, or I guess they ask it in this way, is work being done by the water resistance? Because there is some sort of water resistance here, I'm going to assume that always, especially when the object's moving through the water. Also, I'm tying it to the idea of it being constant speed. Constant speed implies that there is a first law problem. So by first law, we know that the net force, or the F net, is equal to 0 newtons. And so if the F net is 0, it means whatever force that's being applied into the sails must be counteracted by the resistance due to the water on the boat. And so I'm going to draw this piece in here using red. We're going to have some sort of resistant force, which I'm going to call FR. Or you could even call it F2 for all we really care about, but I'm going to call it the resistance by the water on this boat. Okay, now this is going to generate where work number 2, or work 2, is equal to force resistance multiplied by that same distance. Now, what I want you to realize is that these two distances, change in d and change in d, these are equal to one another. And so if we're covering the same amount of distance, and we know that the forces are equal and opposite because the F net must be 0 because it's traveling at a constant speed, the boat's not accelerating, that also means that the two forces must be equal. And if the two forces are equal, that means the two works are equal. And therefore, if I do my works net statement or my W net statement, it would be W net is equal to W1 plus W2. And because these are equal and opposite to one another, they're traveling in the opposite ways. The wind is trying to carry the object, or it's applying a force in the right direction, let's call it. The resistance is resisting in the left direction. We know that these would be equal and opposite to one another. So another way of writing this would be the following. We have W1, which is the positive work. We have plus the negative work being done by the resistance. And therefore, this is going to give us a W net of 0 joules. Therefore, there is no work being done on this overall sailboat. And it all revolves around the idea of if it's traveling at a constant speed, we go back to our Newton's 3 laws of motion, or 3 laws that were around the laws of motion, and we say that if by first law that constant speed means there's a net force of 0, the forces must be balanced over that same distance, no work is done. Okay, now we go into the word problems here. The word problems, there's 6 of them here. I'm going to just go to our next page because I've actually created room to solve these. In your notes, it's kind of the same way. Ideally, I would have separated these out a little bit, but no worries. You can do these on a spare piece of paper. For me, here's what they look like. I've separated them all just by a little bit here so we can solve them all with more room. Now, let's go to the word problem number 1 here, and it's the following. What if we have a 6 kilogram object, or 600 kilogram object, and it's dragged over a 40-meter distance over a surface that has a coefficient of friction equal to 0.6? How much work was done against friction, or how much work against friction was done? That's what we really want to know. So the work done against friction means we have to account for how much friction was there over that distance, and that determines the work required. So when we write this in the formula, we're going to go W is equal to the force of friction, we're going to get specific, times the distance it goes with that friction. Now, in here, we're going to write that work is equal to the FF, which we can transform to mu Fn times delta D, which is then equal to mu Fg delta D. Because this is a horizontal object, we know that Fn equals Fg. And then I'm going to continue up here and say that our work is equal to mu Fg, which is equal to the weight, which is mg delta D. Now, what we can do is we can plug in all the values from here. So we're going to go work is equal to the mu, which is 0.60, multiplied by the mass of the object, which is 600 kilograms, multiplied by the signless g, 9.81 meters per second squared, multiplied by the distance it traveled, which in this case was 40 meters. Now, if I multiply these all out, I'm going to find that the net work, or that work required to overcome this friction, or not necessarily overcome this friction, but in terms of how much work was done by the frictional force in this case, we're going to find that it is 141,264, or 141,264 joules. Written to 2 significant digits, this is 1.4 times 10 to the power of 5 joules. There we go. So this becomes our answer for how much work was done with this frictional force. Now, moving on to our second example, how much work is done in carrying a 40 kilogram object 50 meters horizontally? Now, what I'm going to assume here is that our potential energy stays the exact same and we're traveling at a constant speed. So I'm going to write those 2 assumptions here because this is a bit of a tough one because it's not really implied here. So first and foremost, our potential energy does not change. And meaning there is no change in height. So because there's no delta H, or there's no change in that height, it's staying at this overall height, we're going to assume that there's no sort of EP change. Additionally, what we're going to say is that this is a first law problem, or that there is constant speed. And with constant speed, this means the F net, or the F net, the forces on this are 0. Not the forces on this are all 0, but the net force is 0. Okay, now how this helps us determine the work is that off on the tangent here, or off on the side here, the right-hand side, we say it's the force delta D. There is definitely some distance. We know that there is some sort of change in distance, but in terms of the force, this force by first law, if we know that it's not changing height, that means that there's no sort of change in potential energy, but beyond that, we know that the F net is 0 here. So F net is 0, and therefore we're going to assume that this whole term becomes 0 and that the work is equal to 0 joules, or that there is no work being done here. Now, if they, and this is where it's tough, is that they actually should have said constant speed, because if we said that there was some sort of speed and there was some sort of speed over this given horizontal trajectory, then maybe we could assume it. But we also want to say this too. If it has some sort of net force, a net force implies acceleration. And for this, they didn't imply that there was any sort of like net force or imbalanced force that caused acceleration on this box. And also, you're carrying the box as well. And objects that are carried, often you're not accelerating with that box unless you're speeding up as you go. But we can consider this as a person that's casually walking along with the box in their hand. So it's not my favorite question, but definitely is something worth considering there. All right, now for number 3, here's where we go into that angular work being done, or the angular force happening. So I shouldn't call it angular work being done by an angular force. We have some sort of student that's pushing a broom handle with 20 newtons of force for 30 meters across the floor. If the broom handle is set at 70 degrees to the floor, how much work was done? Now, for this piece here, what I want you to do is draw the broom handle. So the broom handle faces down like this. And then by component method, we know that the first thing or this main force is 20 newtons. So you may want to write this in here, which is equal to the force. Force is 20 newtons. Now, if it's written on an angle like this, namely it's 70-degree force, we're going to break this into the components of we have some sort of vertical force, we have some sort of horizontal force, which is Fx. And I'm just going to write this a little bit off to the side there. There we go, F to X. Now, we know that the angle is 70 degrees, so you want to fill that in here because they said it was 70 degrees to the floor or 70 degrees off the floor. So now when we look at this piece here, we're saying, okay, I have a force that I'm pushing this at, but I only really care about the one force, namely the one force I care about is the Fx, because it's not going off the floor. We don't consider this object to be like floating above the floor or off the floor. So the Fy doesn't really matter to us. The Fx is in charge of this force that causes the overall motion across the horizontal plane. Now, Fx is equal to the F times cos theta. So when we go to our formula for work, we can now understand that Fx is the F cos theta. I'm going to write this as work is equal to, we have force delta D times cos theta. We know that these two, if you really wanted to, you could connect them together and say that this is Fx, but I'm not going to do that because we're given the 20 newtons and we're given the degree. I'm just going to plug it in as is. Work is equal to 20 newtons, which is our hypotenuse, times the change in distance, which the change in distance here is let me make sure, 30 meters, and then multiplied by the cos of 70 degrees. Therefore, the work that is done over this 30-meter distance is equal to 205 joules, which to two significant digits is 2.1 times 10 to the 2 joules. There we go. Excellent. Now, we move on to our fourth problem. So if we, and just as a recap, just before we move on, just to make sure you're okay with this, if they ever describe something at an angle, remember that you're only using the force that is representative of where the object's moving or the force that contributes to that motion. If it's horizontal, the Fy will be balanced with the Fg and the Fn. So we don't need to worry about that. Even if you want to in this diagram, you could put this in. You could be like the N or the Fn experienced by this contact force, the Fg going down like this. We know Fg is equal to Fn plus Fy, so we don't really need to worry about that piece here. Okay, and then because this is being pushed down, the normal force, actually, if I was to be accurate with this, I know this is so side tangent to this problem, or this is such a tangent to the problem, but your normal force would look like this. It'd be a little bit greater because your Fy is pushing down into the ground, meaning there's more contact force, meaning the Fn is increased. So for this case here, you'd be like your Fy plus Fg equals Fn. But again, such a side tangent. I just want you to realize that none of that matters for this problem because all of these three vertical forces are balanced with each other when you would add them in the Fnet for the Y. So we don't need to worry about that. The only force that contributes to this is the Fx. Okay, for number 4, what is the kinetic energy of a car that is 1,200 kilograms traveling at 60 kilometers an hour? Ooh, this right here. As soon as you see this, you need to look at this and be like, nope, I'm not progressing until I fix this. Because if you trip up on this, I'm telling you, it's going to affect your future in terms of your overall ability to do the exams. You need to recognize when they try to trick you with these little things like this. And one of those things that they can do to try to trick you is give you non-standard units like kilometers per hour. We want this in meters per second. The way we can do this is we can use unit analysis or divide the number by 3.6, which will give us 16.6 repeated meters per second. Okay, now if we're just solving for kinetic energy, this problem actually becomes very simple. Kinetic energy is equal to 1 half mv squared, and this is directly off your formula sheet, so you do not have to memorize this. We're looking for that EK, so I'm just going to write this as EK, which is equal to 1 half mass, which is 1200 kilograms. I'm making sure to put in my units, of course, multiplied by the speed, which in this case is 16.6, and I'm going to throw in like maybe 4 decimal places just to ensure accuracy, having the squared on the outside, and the kinetic energy of this problem is equal to, you plug it into your calculator, and it's going to give you a very large number, in particular 166653.3336 joules. There we go. And then we can say that the kinetic energy, when we round it to 3 significant digits, is 1.6. Actually, I want to double check this. Oh, there's only 2 significant digits because of the 60 kilometers per hour. So I'm glad I checked that. This is going to become 1.7 times 10 to the power of 5 joules. There we go. Now, something I want to bring up before we even continue further is the following. Notice how that if I have an object that is a broom handle and I'm pushing a broom across a floor, the work done or the amount of energy in this system is very low. We get a very low amount of energy. Versus when we look at the problems that involve way more massive objects, things like cars and things like the first one here, or the second one here, I should say. Actually, no, it'd be the first one up here where we had 600 kilograms. The amount of energy when we're talking about things that have 600 kilograms and the things that have 1200 kilograms, it's a large amount of energy. So I really want you thinking that the more mass an object has, the more energy we're going to have to apply to that given system to get that object in motion by some amount. That is a very logical based thing to make sure we keep track of here. All right, now for number 5, a spring with a constant of, or a spring with a spring constant of 150 newtons per meter has 4.69 joules of stored energy. By how much has the spring been compressed? Okay, visually, here's what's going on. I'm going to draw the horizontal spring in the following way. So they said we want to figure out how much it's compressed. So I'm going to write this as, there's my spring, here's the mass on the end like this, of this end of the spring, and we're going to write the equilibrium point to be right here. So this would be where our x value is equal to 0. And don't worry, we're going to get more about this into the next lesson. For now, just treat this as a spring will naturally rest in this midpoint of x equals 0, which we sometimes call the equilibrium point, which we will get into. So this is the equilibrium point. And from the equilibrium point, you can either have negative x or positive x. In this case, it looks like we're going to have our negative x displacement because we're going to the left, but on the other side, you could have positive x. And again, I'm overcomplicating this even more because we're not actually going into the spring lesson quite yet, or the springs lesson yet, but I just want to give you a little bit of knowledge here. So they're saying if the stiffness of the spring, and maybe I'll write those key details down. If the K value is equal to 150 newtons per meter, and that represents the stiffness of the spring, and the stored potential energy of this spring is equal to 4.69 joules, so not a ton of energy. What is the distance this covers here? Or what is the distance from here? So this is what they're looking for. How much has that spring been compressed from that given equilibrium point? Okay, now if I look at this here, I'm going to go over here and say the potential energy, or EP, is equal to 1 half kx squared. We're solving for x, so I'm going to start by multiplying both sides by 2, just to get rid of that 2 out of the denominator. This gives me 2EP, which is equal to kx squared. I'm going to get x squared is equal to 2EP divided by the spring constant. And then in order to get that x value, or the compression of the spring, I'm going to write it as x is equal to the square root of that following term. And so when we actually put this in here, oh, I have a lot of room here. X is equal to the square root of, I'm going to start off with the numerator, 2 times 4.69 joules. There we go. And then divided by, in the denominator, 150 newtons per meter. There we go. X value, which is equal to, I end up getting that this is 0.250. And I should check for significant digits. Yes, it's 3. So I'm going to write 0 after this. Done. There we go. So if I was to ask you, this is also the equivalent of 0.25 meters. This is the equivalent of a quarter of a meter. So it's compressed by a quarter of a meter, or 25 centimeters to be specific. Now, 25 centimeters for a spring is quite the distance. So this thing as a spring constant with that amount of energy, it seems very relaxed as a spring. It doesn't seem to be a very stiff spring because we're seeing that it's being compressed by a decent amount. Like if that's the overall compression, that's a lot of distance to be covered for that low of energy, meaning the spring constant is probably not too high, but it's all relative. I don't want to go too much into that because, some of these problems can either be super realistic or, be off by a certain margin. So we're just going to leave it as is. Okay. Now, last one is, what is the power consumed in lifting an object that is 500 kilograms over a vertical distance of 500 meters in a 30-minute time period? Now, right away, I don't like the 30-minute time period, right? Like as soon as I see this is another trick that they're trying to give us here. So let's just fix this here. 30 minutes multiplied by 60 seconds per minute. This is going to end up giving us 1800 seconds. Okay, now that we know it's 1800 seconds, or we have the value in seconds, let's use our power equation to figure this one out. Power is equal to work divided by time. Again, we want to be very specific in saying this is work, not the watts over time. This is going to be equal to the change in energy over time, which is then equal to the change in potential energy over time, because we're talking about lifting an object with some sort of mass over a distance. And then if we substitute this in here, we can write this as EP, which is equal to mgh, or the weight times the height, divided by the change in time. And then putting this all into the equation, I'm just going to go below here, P, which is equal to the amount of power is the mass, which is 500 kilograms, multiplied by gravity to get us our weight, 9.81 meters per second squared, multiplied by the height of this object, which they said it was a 500 meter distance, divided by the change in time, which we found was 1800 seconds when we converted it to our standard units. And therefore, when we calculate our power value, or we put this all into the calculator, we're going to get a watts value, but we get a watts value of 1362.5, or 1362.5 watts. To rewrite this, what we can do is we can either say that the power is equal to 1.4 times 10 to the 3 watts, or we can write this as the following. We can write this as power is equal to 1.4 kilowatts. That is another way of writing this, because if we know it's 1,000 watts, then 1,000 of anything equals a kilo of whatever that unit is. And so we're going to look at this and say we can write it as either the following answer or a kilowatt, either way. And both are totally correct in this case.